In this video, we're going to look at making some conclusions about a function f of x when looking at a graph of its derivative. And this is you commonly see this on AP exams or even maybe some pre-response items, because you have to make that connection about what derivatives are actually telling you in terms of a function increasing or decreasing and the concavity without having the graph of the function to look at. And so what I have here is I made a table that kind of is going to be a little cheat guide for us. And we're looking, so the function y equals f of x will be increasing where the graph of my derivative is doing what? Well, we're talking about the graph of f prime. And we know that a function is increasing where the derivative of x is greater than 0. So where my derivative graph is above the x-axis, so where the graph of my derivative is above the x-axis, y equals f of x will be increasing. And so likewise, f of x will be decreasing when my derivative is negative, which means graphically my derivative will be below the x-axis. And our relative extrema, now we know that a relative maximum for f of x, if I'm looking at a sign chart for my derivative and I have some x value c right here, we're going to have a max where we go from a positive to a negative derivative, or if my graph goes from increasing to decreasing. So if I'm looking at the graph of my derivative, it's going to be where we go from above, if we go from above to below the x-axis. Likewise, we'll have a relative minimum for f of x, where we go from decreasing to increasing, which means my first derivative goes from negative to positive, which means that graphically my first derivative will go from being below the x-axis to above the x-axis. Now, the graph y equals f of x will be concave up, where the second derivative of x is positive. Now, if we're looking at the graph of my first derivative, that means my first derivative must be increasing or have positive slope. And likewise, the graph of f of x will be concave down, where the second derivative is less than 0, which means that the graph of y equals f prime of x will have to be decreasing, since the second derivative will be the slope or the rate of change of the first derivative. Now, f of x will have a point of inflection where the second derivative is equal to 0 or non-existent, and we have a sign change from positive to negative or negative to positive. Now, what does that mean in terms of the graph of the first derivative? Well, what that means is that x equals c will be a critical number of that, because the second derivative is the derivative of the first. So it's a critical number, and we have a sign change where we go from either increasing to decreasing, or the other way around, decreasing to increasing, which means that our graph of f prime will have a relative extrema. And the last part, the slope of the original function at a point, is going to be the value of my derivative. So it's whatever the y value is. Okay, so we're going to look at an example here. A function f is defined and differentiable in the closed interval from -6 to +6. And we're given the graph of f prime. Okay, so we need to make a note of that, of what we're looking for. We're looking at the derivative of f, and then we want to make find some information about f of x looking at this graph. So we'll start with here, what are the critical points? So I'm going to change the orange here. The critical points of f are going to be where my first derivative is equal to 0 or undefined. So basically I'm looking at this graph, and since we're looking at the derivative has values everywhere. I have critical points everywhere it crosses the x-axis. Now I'm only looking from -6 to +6. So we have critical numbers at x is equal to -4 and x is equal to 0, and then we'll just say justifications because the derivative is equal to 0 at those points. Now we're looking to find the relative extrema of f. Well, my relative extrema are going to be where I have a sign change of my first derivative. And so we have a relative extrema at x is equal to -4. Now, the classification of that is going to be a maximum, and then because we go from being above the x-axis to being below the x-axis. So my first derivative changes from positive to negative. Likewise, x equals 0 is going to be a relative extrema. It's going to be a minimum because my first derivative, which is the graph we're looking at, changes signs from negative to positive at that point. So we're still using the justification of that we used before in the previous section, but we're just having to make these conclusions by looking at the graph. Now we want to look at intervals of increasing and decreasing on the from the graph. Now remember, f is increasing where my first derivative is going to be greater than 0. So, and we're on this interval from -6 to +6, non-inclusive. So we're increasing everywhere we're positive. So I'm increasing everywhere I'm positive for my first derivative. So we're going to go from -6 to -4, and then we'd go from 0 to 6. And we're going to be decreasing where it's negative. And so we're going to be negative from -4 to 0, so that interval will be -4 to 0 because my first derivative is negative. That means we have negative slope and are decreasing. Now let's look at concavity next. So were we concave up or concave down? Now, we can determine whether or not a function is concave up or down by what the second derivative is doing. But since we're looking at the graph of the first derivative, we're going to be looking at the slope of our first derivative. So f is concave down. I'm going to abbreviate that. Concave down, where my first derivative is decreasing. So we are decreasing everywhere it has negative slope. And so there's a change in my slope at -2. But I'm decreasing to the left of -2. And I'm also, my first derivative is decreasing to the left of x is equal to 4. And so the interval where we're going to be decreasing is going to go from -6 to -2 and from 4 to 6. Now, likewise, we're going to be concave up where the exact opposite is happening. So f is going to be concave up. I'm going to abbreviate that, where f prime is increasing. So where it has positive slope, but it's going to be everywhere that I did not circle. And so it's going to be increasing from -2 to 4. Now we're going to look for our point of inflections. Where our point of inflection, see, we looking at our change from when our first derivative graph had negative to positive slope, and we have a point of inflection at x is equal to -2 and at x is equal to 4 because my slopes change signs for my first derivative. So we have a point of inflection at x is equal to -2 and x is equal to 4. And our justification will be because our slope of our first derivative changed from decreasing to increasing or increasing to decreasing at those points. And what I did was I highlighted it there so that way you could see, so that at x is equal to -2, the first derivative changed from decreasing to increasing. That's how we knew. And then at x is equal to 4, first derivative changed from increasing to decreasing. And lastly, we have here, if f of -2 is equal to 4, find the equation of the tangent line at x is equal to -2. Well, my tangent line would be y equals, we're looking at the point of tangency, so it would be f of -2 plus the value of the derivative at -2 times x minus -2, or in this case, make x plus 2. Well, we're given that f of -2 is 4. We just need to know what is the value of the derivative of f at that point. Well, f prime of -2, we're given the graph of f prime of x, so we're going to go to -2, and we're going to get what the y value is there. F of -2 is equal to -2, so we'd have -2 times x plus 2. And then you could distribute and put it in slope-intercept form if you needed. That part's not really a requirement, but this one's easy enough. We'll say y is equal to -2x.